So our first goal is to be able to describe a line in 3 dimensions, which is, if you think about it, it's kind of tricky. I can draw a line on the XY plane easily enough, but to try to describe a line in 3D, right, and had an equation form, how would we do that? So I'm going to derive it in 2 dimensions first. So again, make sure you are muted. I hear some extraneous sound in the background. Let's suppose I give you a point, we'll call it, x naught, y naught, and a slope, we'll call it m. So we know that in the xy plane, if I give you a point and I give you a slope, then you can easily come up with the equation of the line using the point slope formula. All right, there's nothing new there. And we know that it's y minus y coordinate equals slope x minus x coordinate. But what I want to do is give a vector description of this. Okay, it's not practical. I mean, the equation of the line is easy enough, but I want to do it in terms of vectors, because if I can figure out a way to describe this line using vectors, then I can easily translate that to 3 dimensions. Because 3 dimensions, it's not intuitively obvious. So the first thing we notice is if I take any other point on the line and call the point just x comma y. X comma y represents any other point on the line. And therefore, we know this is true because if I said, find the slope between the 2 points, you know that you take the difference in the y coordinates over the difference in the x coordinates, and that equals the slope. In fact, that's where the point slope formula comes from. So if I wanted to create a vector using these 2 points, as we saw last day, the vector I'm going to create, it's the vector of differences in the coordinates. So it would be the vector x minus x naught, comma, y minus y naught. Oops, vector, not point. So this vector here, which I'll do like that. Then when I station this here, remember we said all vectors are oriented at the origin. So now this vector here is this, okay? But now this is a line. So I need this to be the same line, but just going through the origin. So how do I make it the same line? Because this is finite, this line is infinite. So one way I can do it is by taking every scalar multiple of this quantity. An easier way to do that would be to notice that if I consider, just take that right there, if I considered the vector 1 comma m. Now think about that vector right there. So if I said go out in this, think of that as 1 and think of that as m, then the slope here would be in fact m. Okay. And then if I said consider every conceivable multiple of this vector. Now m is a constant, m is given, m is not a variable. But if I said consider every value of t positively or negatively, then I would have every multiple of this in both directions. So if I take my original, remember we said x can be any other point on the line, so there's an infinite number of x's. If I set it equal to this, then I'm saying for every real number, or every ordered pair on the line x comma y, the vector created from the given point on that x comma y would always be a multiple of this vector. Remember, this is a finite length. I want to have every possibility. So stare at this for a moment. Does that give us the same thing? Well, one way of thinking about it is if I replace y minus y naught with m times x minus x naught, then I will get exactly this statement right here. So now equate the positions. X minus x naught equals t times 1. Y minus y naught equals t times m. And then from there, I would get x equals x naught plus t, y equals y naught plus mt. Remember, these x and y's are variables. That x and y is a variable, represents every point on the line. X naught, y naught are specific values, it's 3 comma 5 or something like that. So I've now described every x coordinate on my line as being x naught plus t, every y coordinate is y naught plus mt, and a quick check, again, if I replace y minus y naught, okay, with this, then I get the exact same thing again. Or if I replace, actually, yeah, that's all I gotta do. If I replace y minus y naught with that, then I get exactly that statement right there. Or another way of thinking about it, if I replace this t with this t, again, I'm back to here, so I know it's valid. So in the vector sense, this is how I can create an equation of this line. Now, the original line and point slope, right? That using point slope formula is so much easier, no question. But there's no point slope formula in 3 dimensions because there's no slope in 3 dimensions. One thing we're going to discover as we go, slope is a 2-dimensional thing. There is no such thing as slope in 3D. Okay. Okay, you don't. But if I said, okay, in that direction, what's my slope? Okay, now I'd create a plane and then I'd find it. So here's a way of finding the equation of a line using vectors. Impractical, but I can easily translate this now into 3D. So let's do a 3-dimensional version of this. All right, so if I said now in 3D, and again, I start with 2 points in space. Let's call this point P, X naught, Y naught, Z naught, and call that one Q, X1, Y1, Z1. I want to find the vector starting at P, ending at Q. So I want that vector right there. Well, we saw last day, it's the vector of differences of coordinates. You don't subtract points. Points have no algebra. I want the vector that contains those coordinates as a difference. So if I take this and then I move it to right here, what would this vector be? Well, first we call it vector PQ, and it would be the vector x1 minus x naught, y1 minus y naught, z1 minus z naught. Okay, it's that particular one right there. All right, now that's how I create that vector. No big deal. So now let's do what we did before. Now I want to think about the line, not the vector, the line passing through P and Q. So this line is infinite, clearly. The line passing through P and Q is infinite. And so the vector is finite. So I want to consider every conceivable multiple of this vector. Well, if I consider every conceivable multiple of this vector, then what that would give me, okay, first of all, this is the direction. So once I have that, if I consider every conceivable multiple, let's do like we did before with the t. So then what I would have is the vector, let's see, let's do this. This will be my x, this will be my y, this will be my z. So when I take a multiple of this. So now that I have my line, let's call this one here now the generic x, y, and z. All right, any other point on the line x, y, and z. So this q could be here, it could be here, it could be anywhere. So now I'm going to go like this. If I start with a specific pair of points, I do that. If I start with a particular direction, then I can do it like that. But like before, what we want to do is make a scalar multiple of this. Okay, we want to make a scalar multiple of this. And so then I'm going to compare it to, let's call it ABC. Okay, this is this guy right here. And what I want to do is set it equal to this guy right here. This, again, the A, B, and C tells me the specific values when I did my subtractions. So this would be my, again, I want this to mirror what we did in 2 dimensions. So then equating things, I'd have x minus x naught equals a times t. So x equals x naught plus at. Y minus y naught equals bt. So y equals y naught plus bt. And then z equals z naught plus ct. We started with a, b, and c being the direction the line passes through, either by starting with 2 points and then that's my ABC, or by just using the x naught, y naught, z naught and a given direction. So I either calculate this or I'm given this. Then this looks just like what we did in 2 dimensions, but this is now the 3D. So the idea is this. I say, I want you to go in a particular direction. My arm is pointed in a particular direction. When I say particular direction, that means it's automatically oriented from the origin. But I don't want you to start at the origin. I want you to start somewhere else. I want you to start somewhere else in San Diego. Then I want you to go due west 200 feet. Well, to describe the direction, I put it at the origin, but then I take the point in space and I pick my vector up from the origin, I place it at the point in space. So in other words, when I give you this direction, I'm then going to place it at this point, and that gives me my line in 3 dimensions. And see, the x naught, y naught, z naught is how I move off the origin. So unless this is 0, 0, and 0, my line does not pass through the origin. So finding the equation of a line in 3D is actually pretty simple. There's really no calculating, okay? So now we want to find the equation of a plane, which is really, really cool. All right, so imagine that, let's keep it really simple. I have 3 points in space. We agree there's exactly 1 plane that can pass through them if those points are not all on the same line. I would like to be able to find the equation of that plane. Okay, that seems nice enough. But what makes the equation of that plane unique? It's not the points on the plane, it's the direction of the normal line. The normal line determines that. So look at your floor, look at your ceiling. We agree those are parallel planes. If I take a line that's orthogonal to the floor, it's also going to be orthogonal to the ceiling, isn't it? In fact, if I think of layers, or if your house is several stories, think of each floor, they're all parallel planes, but they all have exactly the same normal line. So if you know the direction of the normal line, you don't necessarily know the plane, but if you know the direction of the normal line and you know 1 point on the plane, then you know the plane. Kind of like in 2 dimensions, if you know the slope and you know 1 point, you know the line. Here, if you know the normal line and you know 1 point, then you know exactly what the plane is. So let's do this. Let's suppose I have a plane. This is my 3D plane, okay? I have a normal line. And let's say N is simply A, B, C. A, B, and C being values. I have a normal line and I have a plane. Now, I need a point on the plane. So let's say here's a point on the plane. Let's call it X naught, Y naught, Z naught, okay? And maybe we'll call that point P. There are an infinite number of points on this plane. So let's let X, Y, Z represent any other point on the plane where X, Y, and Z are variables, but that ordered triple is on the plane. Just like when we did the line, we said let X comma Y represent any point on the line. So whatever the equation of this plane is, X, Y, and Z would have to satisfy it. So if I create this vector right here, okay, let's call that Q. Then vector PQ, which is X minus X naught. This is starting to look familiar. We keep doing the same sort of stuff. One thing I do know is that the normal line and PQ have to be orthogonal. Why? Because PQ represents anything on the plane, any line on the plane, or in this case, any vector on the plane, and this is the normal line to the plane. So I know absolutely that if I take N and I dot it with PQ, I have to get 0. If X, Y, Z is a point on the plane, then PQ must be orthogonal to N. So here's what we want to do. We want to do N dotted with PQ, and we want to set that equal to 0. If we do this, this will actually give us the equation of the plane. So in this case here, what will that be? That would be A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. X, Y, and Z are the variables. X naught, Y naught, Z naught, A, B, and C are scalars. So if I distribute and gather terms, I'm going to get AX plus BY plus CZ. Then I'm going to get a constant. Let's just call that D. where D is clearly equal to negative AX naught, negative BY naught, negative CZ naught. This is a scalar also. So this is the equation of my plane. Now notice the original normal line was ABC. Those are also the coefficients of X, Y, and Z. No coincidence. So the equation of a plane always has this form. Okay, it's linear with X, Y, and Z. D can be any real number, including 0. And then I can tell you that the equation of the normal is this. Now, this is really, really simple. I mean, there's nothing about this that in any way is really going to be challenging algebraically, but it's kind of cool stuff. We've just figured out how to write the equation of a plane. But the key is I need a point on the plane and I need the normal line. In other words, I need a normal vector, not normal line, sorry. So let's do an example of this, shall we? Let's suppose that I give you 3 points at random, just 3 points in space. Here's what we want to do. Find an equation of the plane passing through, let's say P is -1, 2, 0. Q is 3, -1, 2, and R is, I don't know, how about 4, 1, -1. I want to keep the numbers relatively small. Here's 3 points in space that are not all on the same line. There can only be one plane that passes through all 3 of them. I want to find an equation. Yeah, I said an equation. Think of lines for a moment. There's only one way you can write a line in slope-intercept form. But whatever that line is, if I decide to multiply both sides by a scalar or add an arbitrary constant to both sides, it's the same line, just a different form, meaning there's an infinite number of representations of any line. Just, do the same thing to both sides of your equation. Well, the same thing is true with a plane. There's an infinite number of representations, although there would certainly be not very many that we would consider to be useful. So I got to find a plane. Well, how am I supposed to find a plane? I need a normal vector. Well, the normal vector I can get if I know 2 vectors on this plane, my arms are vectors, and I take their cross product, I know that will give me the normal. So all I need to do is take a cross product. But I don't have any vectors yet. So we will create 2 vectors. I have P, Q, and R. So let's say there's P. Let's say there's Q. Let's say there's R. Then I need to find the vector PQ and PR. Then when I do their cross product, I will get my N. Okay, that's how it works. So, and by the way, it doesn't matter if I say PQ or QP or QR or RQ. I just need the same point to be the vertex. So I'm just going to be lazy. I'm going to do PQ and PR. It's just easier for me to keep track of. So the vector PQ is 3 minus -1, -1 minus 2, 2 minus 0. The vector PR, 4 minus -1, 1 minus 2, -1 minus 0. Okay, actually, let me write it. I'm going to put it under. Makes my life a little easier if I do this. All right, so here are the 2 vectors I created by taking the 3 points and making P be the vertex, and I got these 2 vectors. I now need the normal to this plane, and the normal is simply going to be the cross product. So the normal vector, which will be PQ cross PR, okay, 3 minus -2, 10 minus -4, -4 minus -15. Okay, that's it. Now, I want to make absolutely certain that that's correct, because making errors at this point is, well, it's an easy thing to do. So let me do the dot product with either one of these two. So 25 minus 14 minus 11, that is in fact 0. Or I could have done this, 20 minus 42 plus 22, that is also 0. I have absolute certainty then that this is the normal vector. Okay, please mute yourself. Especially when I hear the kids in the background, it means you're really distracted. All right, now how do I get the equation of the plane? Well, I have my normal vector, I just need one point. Well, which one? Doesn't matter. All three of them should give me the same equation. So I'll use this one. All right, so we're going to do then, remember how we did it before, x minus x coordinate? So it's going to be 5 times x minus -1 plus 14 times y minus 2 plus 11 times z minus 0, and that has to in fact be 0. So I'm going to distribute. Five minus 28, that's -23 plus 0. Now, if I didn't make any mistakes, that's the big if, then this is an equation, probably the most efficient equation. Is it possible I've made an error? Is it possible I distributed badly? Is it possible I got my negative signs all messed up? Yeah. Every error imaginable is possible. How can I be certain then that this is correct? Well, first of all, I see evidence of my normal vector. Okay. All three of these points have to satisfy this equation. Now, since we used this point to create the equation, we pretty much know that point's going to work. So let's use a different point. Let's say I use this point as my check. So 5 times 4 plus 14 times -1 plus 11 times -1 minus 23. Okay. Did I write that correctly? Oh, sorry, 14 times 1. So 5 times 4 is 20 plus 14 minus 11 minus 23. So 34 minus 34 equals 0. Okay. Always do a check because checks are so easy to do. So finding the equation of a plane is as simple as taking a normal vector and one point on the plane and then creating it. We didn't start with any vectors. We started with 3 points in space. We created 2 vectors. We took the cross product of those 2 vectors, and then we came up with this. So now here's a question. What if I did PQPR? What if I had done QPQR or RPRQ? In fact, what if I reverse the order of the cross product? Will I get the same plane? Well, something as simple as reversing the order of the cross product, because that order is completely random. If I reverse the order of the cross product, remember we get the negative of this vector. Is that the same thing? Well, if I got the negative of the vector, then basically it's equivalent to multiplying both sides of this equation by -1. So it'd be -5x, -14y, -11z plus 23 equals 0, which we know is the exact same equation. In fact, all the conceivable rearrangements of P, Q, and R, and all the ways I could have done the cross product, again, it could be PQ cross PR or PR cross PQ, and then I can do that for all 3. There's exactly 6 ways I could have set up to find n. 3 of those ways would have produced this vector. 3 of those ways would have produced -1 times this vector. So that means I would have gotten this equation or the opposite signs equaling 0, which is, again, the same plane. That's why I said find an equation of the plane, because technically there's more than one way I could write it that's still the same plane. So this is very, very powerful, that I can say that given any 3 points, I can find the equation of a plane. That's a piece of cake. Now, a secondary thing that I might be interested, because now I'm in space, and I got 3 points in space. 3 points in space, P, Q, R, in space. Don't they uniquely determine a parallelogram? Okay, that's a terrible parallelogram. Let me try that again. I can do circles and spheres. I'm not very good with line segments. All right, there's a parallelogram. How do I find the area of that parallelogram? Well, if you remember, the area of the parallelogram was equal to the length of the cross product. We proved that last day. Oh, so remember, if I'm thinking of these guys as vectors, then the area of this parallelogram is nothing more than the length of the cross product. So what's the length of the cross product? That would be 5 squared plus 14 squared plus 11 squared. So that'd be what, 25 plus 196 plus 121. So what's that? 352 under the, or excuse me, 342 under the root. Now, does that factor down? Yeah, I believe we can probably pull quite a bit out of that one. Let's see. I believe this would be, I definitely pull out a 9. So I think this would be root 9, root 38. So if you want to reduce that, so 3 root 38. So if I said, what is the area of the parallelogram determined by those 3 points? You'd say it's this. What if I'm not interested in the parallelogram? What if I'm interested in the triangle? It's just 3 points. If I said, what's the area of the triangle that these 3 points determine in 3 dimensions? Now, if you could only imagine, if I give you 3 points an hour ago, before we did this, if I gave you 3 points in space and said, find the area of the triangle, well, you'd have to use the distance formula. You'd have to figure out the angles. That would be quite an undertaking to try to figure out that area. In fact, if it's not a right triangle, it'd be really hard to figure out the area. I mean, you could eventually brute force it. Or I could just say, well, it's half of this number, because the area of a triangle is half the area of the parallelogram. So if I said, what's the area of the triangle determined by these 3 points? You'd say it's 3 halves, root 38. Oh, okay. That's not that bad. Okay. So that's some cool stuff we can do with planes. And that's not all we can do with planes. So let's keep going. There's no calculus in this. It's just real simple geometry so far. Now, here's a really good question. There's an object up in the air. Maybe it's a bird, maybe it's a plane, maybe it's Superman. I don't know. There's an object up in the air. You'd like to find the distance from the object to the ground. You'd like to find how far away or how high up in the air is that object. How would you do that? Especially if the object's not directly over me. So of course the object has a big, rope hanging from it, and we know exactly the length of the rope, and we can just, calculate. Well, probably not. So if an object were up in the air, here's the ground, here's me. Not a very good version of me. Here's the object up in the air. I want to find this distance. Well, can I use something in here? Well, you remember in trigonometry, things like angle of elevation and all that kind of stuff. All of that stuff was very, very, very powerful stuff. Okay. Hopefully you remember things like that. You want to find out the height of a tree, use angle of elevation. All those are really cool things, as long as we live in a 2-dimensional world. The problem is angle of elevation is kind of tricky if I'm in 3D, because where am I measuring the angle? It's as I'm turning, it's a little different. So instead, what if we used vectors? What if we used vectors and try to do something that way? So I'm going to show you something. All right. Let's suppose, this is dying on me here. Do I have another eraser here? Okay. A little bit better. Okay. So I'm going to draw a picture, and I want to figure out, if I can, okay, again, this is my infinite plane. And let's say this plane has the equation ax plus by plus cz plus d equals 0. I know the equation of the plane. That's not in doubt. So what I'm going to do, I have a point not on the plane. Let's call that point, I don't know, how about point Q? And point Q is going to be, let's say, X naught, Y naught, Z naught. This is a given point. I want to find the distance from this point to the plane. So in other words, I want to find, let's say that's the distance right there. Call that the height. Okay. I want to find that distance right there. And all I have is the equation of the plane. So like I said, that thing is flying up overhead, but it's not necessarily directly above me. And I'm trying to find the distance from something to the ground. Well, I do have the equation of this plane. And I do know that the normal line, or excuse me, the normal vector is A, B, C. How do I know that? Because that's how we got this equation. So let's say right there, there's my N. And let's say here's a point, lack of a better name, let's call this point P. And let's say P is X1, Y1, Z1. P is any point that satisfies this equation, but P is going to be, think of P as a particular point. P is going to be any point that satisfies this equation, okay? P is not directly under, under Q. Nope, not at all. Okay, so what am I going to do in this case here? Well, what if I said, let me draw that vector. That vector is PQ. Okay. Let me kind of. Again, I'm trying to find the distance that this is to the plane, and I'm just going across the plane to find another point. I can find this distance. That distance is a piece of cake. That's because I have that and I have that. I'm trying to find that. Well, how the heck am I going to do that? Well, the question is, how much of this, because remember, the normal points straight up and down. The height is straight up and down. In other words, these are both orthogonal. How much of the normal vector is here, or how much of this is in the direction of the normal vector? That's a simple projection. Oh, and the easiest way to do that is with a dot product. So if you guys remember this, so how much of this is in this direction? So if I went up like this, how much of this is in this direction is the height? How much of this is in this direction is the height? And so the easiest way to do that is to do the dot product of PQ, but not on N, on the unit vector in the direction of N. So this is something we did last day. So my height will simply be the unit vector in the direction of N dotted with PQ. Oh, piece of cake. Now, if H just so happened to be directly above, then the angle between them would be 0, and that would be an easy thing. Here's the beautiful thing about this. We already know this from last day. Think of it as my refrigerator example. When I said, push a refrigerator off at an angle, how much got done in the direction I wanted, right? It's the dot product. So that's why if I moved completely sideways and I said, how much did I get done across the room? You said the answer was 0, because the dot product would be 0. Remember, length, cos theta. So I need to do this. Now, there is one small potential issue. If I gave you an equation of a plane in 3 dimensions, so here's my plane in 3 dimensions. Pretend this is infinite. And I said, how far is this point to the plane? And you're doing all of this problem. Everything's wonderful. But what if my point was on the other side of the plane? How do I know which side of the plane I'm on? I don't. Oh, so when I'm creating this situation here, and that's my normal vector, what if this point is on the other side of the plane? Then that means that I would have an obtuse angle. Oh, and if I had an obtuse angle, doesn't that make the dot product negative? Oh, yeah, it's possible for the dot product to be negative. Darn. So how do I fix this? Absolute value. And here's why. There's an infinite number of ways I can ask the question. And exactly 50% of the time, your dot product is going to be negative. The other 50%, your dot product is going to be positive. Yeah, so by the way, what if the point I gave you, just hypothetically, was actually on the plane? Oh my gosh. Well, then this would be a right angle and you'd come up with a distance of 0, which you should if it's on the plane. So this is what I need to do. I need to do exactly this thing. And it turns out this will reduce beautifully. So let's start with this. That's going to be 1 over the square root of a squared plus b squared plus c squared times the vector a, b, c. That's the unit vector in the direction of n. We're going to dot that with pq, which is the vector x naught minus x1, y naught minus y1, z naught minus z1. All of this in absolute value. Okay, so when I do that, I'm going to get a times x naught minus x1 plus b times y naught minus y1 plus c times z naught minus z1 in absolute value over the square root of a squared plus b squared plus c squared. Now I don't need absolute value because that square root is strictly positive already. Now, my numerator looks very, very busy right now. But if I distribute and gather terms, you're going to know something really cool take place here. Really cool. Let me distribute and gather the naughts, if you will. So I'm going to have ax naught plus by naught plus cz naught minus the quantity ax1 plus by1 plus cz1. Okay, all in absolute value, all over this. We're almost done. Now tell me about x1, y1, z1. Isn't x1, y1, z1 a point on this plane? That means x1, y1, z1 satisfies this equation. So if I replaced x with x1, y with y1, and z with z1, then I would get ax1 plus by1 plus cz1 plus d equals 0. That means this quantity right here, when added to d gives me 0. That means this quantity right here is, in fact, negative d. So after all of that, this is going to simplify to ax naught plus by naught plus cz naught plus d you notice it's plus d, and the reason it's plus d is because if I throw the d on the other side, this quantity equals negative d, but it's minus this quantity. This equation right here, remember, you're given x naught, y naught, z naught, and you're given the equation of the plane. This is just plug and chug. This is one of the simplest formulas we'll ever derive in this context. So it's beautiful. If I want the distance from a point to a plane, that's all I got to do. I just need the equation of the plane and the point that I'm interested in. Now, again, the absolute value, because this quantity can be negative and you're finding a distance, right? And we know distance can't be negative. So let's do a simple example of this. Let me grab a paper towel here. It's getting harder and harder to erase this as I go. Okay. So let's suppose, let's say we want to find the distance from the point P, let's say -3 to 4 to the plane 2x minus 3y minus 4z plus 6 equals 0. Keep it real simple. I'm giving you a plane. Now, it's not necessary that you try to envision what this plane looks like in 3 dimensions, right? That'd be really difficult. I just simply, the formula. Now, hopefully I did not choose something where it's actually on that. Let me do a quick check. -6, -6, -6. Okay. It would be lousy if I picked a point that was actually on that plane. All right. So what we're going to do, our formula, you can say it's distance or you can say it's height. It really doesn't matter. I don't want to use D for distance because we were using D in the formula for the plane. AX plus BY plus CZ plus D equals 0. That's why I think most authors will use an H. So H is, well, first of all, what's my normal vector? That would be 2, -3, -4. So my denominator is going to be the length of this. So 4 plus 9 plus 16 under the root. On top, now what am I going to do? On top, I'm going to do the formula that we just derived, right? So we're going to go AX1 plus, and so on, or in this case, X naught. That's my X naught, Y naught, Z naught. So it's going to be -6, -6, -16, plus 6, all inside of the absolute value. And I do need the absolute values because that quantity is in fact negative. So -12, -28 plus 6, that's -22. So the absolute value is just 22. 13, 16, that's 29. That's it. Now, if I could reduce that, if I could find a common factor, if anything I can do, I'll do. That's a perfectly acceptable final answer. Notice that I took the absolute value in order to get that. Don't state the answer as the absolute value of a negative. Just go ahead and evaluate that absolute value. So now we figured out a whole bunch of things today. We know how to write the equation of a line in 3 dimensions. We know how to write the equation of a plane in 3 dimensions, and we know how to find the distance from a point to a plane. Kind of beautiful stuff. Last day, we looked at how to find the distance from a point to a line in 3 dimensions using cross product and such. So let's continue now. We're done with the lines and planes portion. Now we're going to begin a new little section where I'm going to deal with what are called surfaces. And this is actually quite simple. Now, if you look ahead on Canvas, I've already posted lots of notes and lots of videos on the stuff that I'm talking about. So there are videos on the lines and planes, there are videos on the surfaces, and you don't have to watch them if you've come to the lecture, but it's some extra stuff, supplemental stuff. So let's consider that I want you to sketch the graph of, let's say, x equals 2. I want you to sketch the graph of x equals 2. Well, it's kind of ambiguous because that would be a correct graph. On the number line, I've just graphed x equal 2. Okay. Or, actually, let me change that. Let me change that to y equals 2 because it's going to make the next part a little easier. What if I did the xy plane? That being 2 units up. On the number line, y equals 2 would be one number. On the xy plane, y equal 2 would be this, and then the coolest one of all. The reason I'm going to do a y, it's a little bit easier for me to draw that one. What if I do this guy here? I'm going to go 2 units out on the y-axis, and then I'm going to draw that plane. So this plane is coming out at you. The x-axis is coming out. This is y equal 2 in 1 dimensions. This is y equal 2 in 2 dimensions. This is y equal 2 in 3 dimensions. Now, you didn't realize y equal 2 is a plane if I'm in 3D. So if I just said draw y equal 2, it's a little ambiguous. You'd have to know what dimension you're in. Now, this is very important. So it always starts with we have to know what dimension we're in. Okay, so we're going to be talking today about what are called surfaces. Well, a surface automatically implies that it's 3-dimensional. Okay, there actually has to be, if I have a box, I can talk about the different surfaces. But if I have a piece of paper, we just have the one, right? It lives on a plane. So we don't think of it that way. So if I continue with this concept, what if I would like you to draw, let's draw the graph of how about x squared plus y squared equals, I don't know, 100. Well, I know what that is. That's a circle of radius 10. Okay, great. So all right, that's 10 units. So that's negative 10. I'm not going to bother putting a little. All right. So we agree. There's a fairly accurate depiction of that if I'm in 2 dimensions. Is it possible I could be in 3 dimensions? In fact, the default usually is that you're in 3 dimensions. So how would I represent that thing if I'm in 3 dimensions? Same circle right here. Now I'm in 3 dimensions. Oh my gosh. This is a circle on the XY plane. This would be a circular cylinder in 3 dimensions. It would be a circular cylinder where that circle right there is that one. But I'm also going up and down forever because there's no Z coordinate in the equation. When you drew the line on the XY plane, you drew that infinite line. Since there was no X, you just went forever in X direction. There was no restrictions. There's no Z, so I go forever in the Z direction. Whoa. It'd be the equivalent of if I had Z coming out at you, then I'm pulling this thing out at you. So this gives us the basis of defining something in a moment. Okay. This is the concept of a cylindrical shape. Now, the mistake most people make when they hear the word cylinder, they automatically think of this shape right here. This is a circular cylinder. There's an infinite number of cylindrical shapes. You see, what if this was an oval rather than a circle? What if it were an ellipse? Then it would be an elliptical cylinder. Oh, so I can have different variations. So I'll give you an example. If I said, y equals x squared, we know what that looks like. That's a piece of cake. Well, in 2 dimensions, sure. Who said we're limited to 2 dimensions? You mean that can be a 3-dimensional shape? Yeah. By the way, you're never going to be asked to draw a shape. But you do have to know what the shapes look like. In Calc 1, you had to know what the graph looked like, or you would never been able to create your boundaries in order to find areas and things of that nature. In this class, you have to know what the thing looks like for the same reason. Finding boundaries. If I want to find surface areas or distances, or I want to find volumes of enclosed shapes, I have to know certain things. Now, how in the world could I make this thing work? Well, let's find a different color pen here. I'm not much of an artiste, but I think you guys can kind of figure out what's going on here. In this case here, whoops. Yeah, I think you guys can see it. It's my parabola going this way. This is what we would call a parabolic cylinder. Okay. Parabola, parabolic cylinder. If I took this parabola, I said, let's go forever, kind of creating a trough, as I'm coming out at you, that's essentially what that is right there. This is going forever in the Y direction. So if I'm standing on top of the Z axis and I'm looking down, I see this. This is what I see. So the concept of a cylinder, I'm going to reinvent what you think you know, because we're going to get it right. The concept of a cylinder is real simple. A cylinder is 2-dimensional extended into 3. And what I mean by that is the equation of a cylinder generally only has two variables, but you're going to extend it into three dimensions. So if I said, consider this nebulous piece right here. Now, I'm going to take this and I'm going to pull it out forever. So this nebulous blob would form a blobular cylinder, lack of a better name. If that were a circle, circular cylinder. If that was a parabola, parabolic cylinder. If that was an ellipse, elliptical cylinder. We describe a cylinder based on this shape. Now, here's the rule of a cylinder. Think of this like cookie dough. I have a big mound of cookie dough. If I make all of my slices parallel, then all of the slices are congruent two-dimensional shapes. And that's critical. They have to be the same. Every slice is exactly the same shape forever. So if I brought this out forever, then all slices parallel to the wall here would look like that. That's why when we have the circular cylinder, it's like circles being stacked upon each other, my parabolic cylinder and so on. So it's not necessary that you can draw something in three dimensions. It's necessary that you can correctly describe it because you ought to be able to see it up here. Okay. So if I asked you what something was, so if I said something like this, I've got x squared minus y squared equals 1. I know what that is. That's a hyperbola in two dimensions. But what if I said this is a surface? Now it is no longer a hyperbola because it's no longer two-dimensional. So the key word here is the word surface. If I said, what is this surface? You say, well, it still looks like a hyperbola, doesn't it? Exactly. So it's a hyperbolic cylinder. If I'm saying surface, well, in two dimensions, I know this is an ellipse, so this is it's actually that simple. If you know it's a surface and there's only two variables given, then it's that type of cylinder. And usually we keep it simple. We do a lot with conic sections because we can conceptualize conics a lot easier than other things. If I put higher degrees on here, it'd be a little bit harder. But the fact is the two variables and it's a surface automatically makes it a cylinder. So whatever the surface looked like, or I should say, whatever the shape looked like in two dimensions, imagine now you're going to extend that forever. There's no limit because if there's no Z, now these are an X and Y. What if I said, I want y squared plus z squared equals 1. What would that be? Well, I'm still asking for the surface, so it is still a circular cylinder, but it's not the one I drew before. What's the difference? Well, what's the missing variable here? There's no X. So it is a circle. So this is how we start the problem. It's a circle on the YZ plane. Remember, there's X, there's Y, there's Z. So it's a circle on the YZ plane, and then it extends infinitely in the X direction. How do I know that? Because X is the missing variable. So therefore it goes forever in the X direction. It can't go forever in X and Y, or excuse me, Y and Z. I mean, Z's got to stay between -1 and 1. Y's got to stay between -1 and 1. Now, I'm not an artist. I don't pretend to be one, but this is a really simple and accurate representation of what it is we're actually trying to find. Okay, hang on one sec here. Grab something. Okay, so make sure I got everything covered. Now, today I'm doing the easier version of the surfaces. Next day, we're going to do the surfaces that involve three variables. So something like a sphere at that point, a little bit different shape. What I need you to get out of today then is the ability to come up with the equation of a plane or the equation of a line in three dimensions, certainly finding distances and being able to identify simple surfaces that only have two variables involved, knowing now that's the definition of a cylindrical shape. So I will go ahead and stop here. I think. Hold on.